Hi, I'm Julie and I'm a project engineer here at Vibes. Today I'm going to show you how to use our awesome software for FRF testing, Dirac. Within Dirac, you can prepare, measure, and analyze your FRF data all in a convenient workflow. Let's begin with the measurement preparations. Here you can see the structure I'm going to be testing today. It's the steering gear of a car, and I want to measure FRFs at the attachment point so I can couple it to the rest of the vehicle using dynamic substructuring. You can see that I've already set up some accelerometers and marked some impact points around the structure. Now we're going to replicate this setup virtually in Dirac. First, I'm going to drag and drop an STL file to load the geometry. In the 3D environment, I can easily navigate around the geometry and change the colors and other properties of the components. Now I'm going to add some sensors and impact points to the test. Here you see the sensor database where I can add accelerometers, microphones, hammers, and custom sensors. Selecting the sensor I want, I can drag it around the geometry and attach it at the right place. Since it's glued to the STL file, the positions and directions are automatically determined. Similarly for the excitation points, I can drag them around the geometry and place them where I'm going to be impacting. Now I can add a virtual point in order to get FRFs exactly at the interface. By selecting some sensors and pressing V, a virtual point is placed at their geometric center. If I now go to list mode, I can see the coordinates of all my sensors, excitations, virtual points, and geometries. I have the actual coordinates of that interface for my finite element model, so I'm going to paste them in here. Now let's make sure all the sensors and impacts are tied to that virtual point. And it looks like this interface is ready to go. Let me just do the same thing on the other side and set up the rest of the measurement really quick. Now that the test is set up, we're going to begin live testing using Mueller's MK2 data acquisition system. If you don't have access to an MK2, you can still do your test separately and then import your results afterwards. However, as you'll see, the integrated FRF testing in Dirac is really one of its key features. Let me show you. Here we can connect to the MK2 using either its IP address or a cloud station. Next, I need to define my input sources. In this test, I'm actually going to use two different impact hammers that excite different frequency ranges and then crossfade the results. Here I also set my FFT parameters. Next, I need to map the sensors. Here you can see how Dirac automatically recognizes my hardware setup, so I can drag the sensors and hammers directly to where I've connected them. On this page, I have some typical channel settings. And then lastly, I can set my windowing. Now I'm ready to begin testing. You can see how the excitation I'm working on is highlighted. Let's do a few impacts. I can collect as many impacts as I want and then toggle individual ones on or off or delete them. I can also use the arrow keys to easily review all of the different responses. This allows me to review the response spectra as opposed to the input spectrum. Going to the next point, you see again how the right excitation is automatically highlighted in the 3D viewer. Of course, the overloads are detected and automatically not included. Now I'll just finish up the rest of this measurement. Now that I've used two hammers, you can see in the input spectra how they excite different frequency bands and are automatically crossfaded together within Dirac. Now that we've taken some data, it's time to analyze it and see how good we've done. Using the 3D matrix viewer, we can quickly get an overview of the complete dataset. Here I'm using it to review the average coherence up to 2000 Hz, but as you can see there are also some other options. My coherence is really good, but I can zoom in to see which impacts are the worst. I can easily toggle specific impacts on and off to get the best coherence possible. Another useful feature is the animation of the operational deflection shapes. I can review the ODS at different frequencies to ensure my sensor orientations are correct and to get immediate insight into the dataset. Lastly, we can switch to virtual point mode, where the FRFs are now true driving points and also capture rotation. Here I have some more insights into the data quality and whether or not my sensors and impacts are behaving consistently. Hopefully now you see how Dirac can improve the whole testing process. If you'd like to learn more about Dirac or anything else we do here at Vibes, get in touch by sending an email to info@vibestechnology.com. Thanks!